The, um, the goal of today's, or this particular section of today's lecture, is to talk about the Euclidean algorithm, but I think you can't really discuss an algorithm without knowing what it's about or what it's for. So this is section 2.2 in our book, and it's titled Greatest Common Divisors. Greatest Common Divisors, but I think that may be the last time you see me write that out all the way. Usually we just abbreviate it as GCD. In fact, I often even elide the points in between them, just write GCD as if it was a word. Here's the definition. Well, let's take it a step at a time. If D is a number that divides both A and B, well, wow, I should have started this off by saying given integers A and B, excuse me. We say D is a common divisor of them, provided it divides both of them. So D divides A and D divides B. And the only other thing you need to make it be the greatest common divisor is for it to be greatest. So that's the definition of greatest common divisor. If additionally D is the largest such number, well, that means that it's the GCD. We usually write GCD as if it were a little function like sine or cosine, but it's a function that takes two arguments. So it looks something like this. D is equal to GCD of A and B. Now, there's something I wanted to remark about here. This is a little bit like the well-ordering principle, but turned upside down. That is, if you think about the collection of common divisors of two integers, there's a cap on how big they can be. I mean, the smaller of the two integers is the biggest thing that could be a common divisor of both of them. So this is a set of natural numbers that's bounded from above. There's no way to get above a certain point. If B is the smaller of the number, then the biggest D could be is B, and be a divisor of both A and B. So we have a set that's bounded above, it's discrete, and it's like the natural numbers. Just turn the well-ordering principle on its ear, and it tells you there has to be a biggest element of such a set. Just like in the well-ordering principle, there was a smallest element of a set that was bounded below. Right, so D is it. D is whatever that largest set amongst, that largest element amongst all the common divisors is. Now, I think we should do an example. Maybe the book starts off with 6 and 10, which I think is maybe too easy of an example, but we could try that, I suppose. What's the GCD of 6 and 10? Well, what you want to do is figure out what are all the divisors of those numbers. Now, the divisors of a number actually have a nice structure that you should know about. They form what's known, or you can write them in what's known as a Hasse diagram. 1 is always a divisor of any number, so that belongs at the bottom of your Hasse diagram. And the prime factors of your number will appear at the next layer. And then, gee, I kind of want to have it go right up to where the loop of that G is. Can I make this G's loop go over there? Okay. the 6 would go there. So these are all the divisors of 6. 1, 2, 3, and 6 itself. You've got, this time I'll start off at the top. 10 will be the number at the top. The prime factors are 2 and 5, and then 1 at the bottom. Now, don't get the impression that the Hasse diagram of divisors is always a little diamond like this. For instance, if I had 30, its divisors, well, you think about the prime factors. 30 is 2 times 3 times 5, so you have prime factors 2, 3, and 5. Pairs of these, they'll give you products that are also divisors. So 2 times 3 gives you 6, and the way this works is 2 and 3 both divide into 6, and 6 divides into 30. Let's see, 3 and 5 both divide into something. That would be 15, right? And there's one left. Oh, 2 and 5 both divide into 10. Wow, my writing on those dashes was terrible. And then 15 goes into 30, 10 goes into 30, and I've already said 6 goes into 30. My picture is maybe a little bit sloppy, but if you look at it just the right way, you may notice this looks like a cube standing on edge. And there's other geometries that you can get as the collection of divisors of a number. Anyway, here's our two Hasse diagrams. That's the complete set of all divisors of 6 and the whole complete set of all divisors of 5. What's the biggest thing that's in common between them? The only common divisors are 1 and 2. And the biggest out of 1 and 2 is 2. So you can do this by brute force. Just write out all the divisors, look for the largest element that's in between the two. That might not be the most clever way to go, but it is certainly a way to go if the numbers are small enough. Let me give you an example that's a little more challenging. 60 and 84. Okay. So GCD of 60 and 84. And you saw from those listings I made of the divisors of, what was it, 6 and 10, that there's something to do with primes in here. So one way to get at GCDs is to go and just factor the things, figure out what the prime factorizations are. You've probably done this before a lot, so I'll just sort of sketch for you how that works. You build what's known as a tree, where you peel off factors. For instance, I noticed that 60 is even, so I peel off a 2, and then what remains is 30. Well, 30 is even too, so I peel off another 2, and then what remains is 15. 15 is not even, but it is 3 times 5. So you make this tree where you pull out the factors, and this, we know that there's 2 2s, a 3, and a 5 in the factorization of 60. In other words, 60 is equal to 2 squared times 3 times 5. I'm sure you've done that before. Let's pull the same thing with 84. 84, again, it's even, so you peel out a 2, and what remains behind is 42. That's even, so another 2, and that leaves you 21 when you divide 42 by 2, and 21 is 3 times 7. So 84 is, oh wow, it's also got 2 squared, 3, and it's got 7 instead of 5. So it's got a very similar shape. Now, once you've got prime factorizations written down like this, you spot the common divisor, the greatest common divisor, by sort of looking at what primes do they have in common. They both have 2. In fact, they both have 2 2s. Both have 2 squared as a factor, and they both have 3. So you can spot the common divisors right in there in terms of the prime factorizations. 2 squared times 3 is 12. That's your GCD. It's sort of the largest collection of prime powers that are in both numbers. Surprisingly, I mean, personally, if I was an ancient Greek, I think the biggest numbers I'd ever have to deal with would be things like 60 and 84, and this is more likely what I would come up with as a an algorithm for producing GCDs. Figure out the factorizations, and then look for the common primes between them. So, in fact, in this book by Euclid, they didn't do this. They figured out an algorithm that produces it. And what's amazing to me is that for small examples like this, what I've done here is usually quicker. But nowadays, in modern cryptography, we need to sometimes find the GCD of two numbers that have 400 digits in them. And doing this, finding the prime factorizations, is already impossible, right? And so you can't even get started on doing the process I've just tried to play with numbers that have 400 digits in them. But the Euclidean algorithm that these guys that invented, way before computers, I mean, most people were probably herding goats at this point in the world, and it works. It works now, today, on things that have 400 digits in them. You can find the GCD of two 400-digit numbers in a few milliseconds. Surprise. So they were ahead of their time, these ancient Greek mathematicians that thought up the Euclidean algorithm. It probably was not Euclid. He sort of gets credit for a lot of things. It's not even actually known whether Euclid was one person. It may have been sort of a name that a group of people used to publish things under. But, yeah. All right, so my mind is boggled by the example of Euclid. So let me show you one of the theorems in our textbooks. It's number 2.2.4. And this is a great example of a TFAE proof, although Dr. Chrisman doesn't use the TFAE formalism. 2.2.4. What he basically says is there's three distinct ways you can think about the GCD. And given the different situations, you'll want to use one or the other of these things. And that's where a TFAE proof, I should tell you what I'm talking about when I say that. TFAE stands for the following are equivalent. So in a TFAE theorem, you're saying here's a bunch of statements that all define the same notion, or that are all equivalent to one another in a logical sense. So what's going on in theorem 2.24 is there's three different ways to look at the GCD. So given, and they're all equivalent, right? Given A and B, let D equal the GCD. And these are the statements that are equivalent to one another. One is what I just said two boards back about what's the definition of the GCD. D is the largest number that divides A and divides B. I guess maybe I should say integer. So that's what most people take as the definition of the GCD. Fine. That's one of the things that is an equivalent statement to the other two. The second one is that, and this is presaging something that's coming in a second, but D is the output of an algorithm. D is an output of D is the output of the Euclidean algorithm. I mean with inputs A and B. I guess I should probably say that, if that's what I mean. And the third thing is not going to fit on the bottom of the board, is it? But I'll stretch to the top of the board and see if we can get it in here. 3 is this. D is the smallest element of a certain set. Well, let's put it this way. We'll make a set that is integers, so it could be positive and negative, but D will be the smallest positive entry. And the set I'm going to talk about, or I'm talking about here, is a little bit strange looking. It's something known as the Z module generated by A and B. So it's the collection of things that look like AX plus BY, where X and Y are integers. So this has a nice geometric character. You can think about every point in the XY plane. You write a number there. That's this computation. You know, you started out with A and B. So A times the X coordinate plus B times the Y coordinate gets written at the point XY. So that's a huge collection of numbers. You know, sometimes both X and Y will be negative, so these will be negative values. You can probably figure out, let's see, if X was B and Y was A, then, no, wait, did that wrong. If X was B and Y was negative A, you get 0 out of that. So it's important that we're looking for the smallest positive integer, not natural number, because 0 would always be the answer then. Anyway, this collection of multiples of A and B has a least positive integer in it. Intersect this with the natural numbers, and then the well-ordering principle tells you that there's a least element in it, and that turns out to be the GCD. So this result, or this theorem, we haven't actually proved it, but in fact, I don't intend to prove it, but it's remarkably powerful. If you've got a statement that's just about GCDs, and it's amenable to just using the fact that you're the largest number that's a common divisor, then you can use part 1. If you've got something algorithmic and you need to say something about the output of an algorithm, then use part 2. And this version of it is, well, when you take abstract algebra, or if you take abstract algebra, you'll find you use that sucker over and over again, that you can write the GCD as a linear combination, an integer linear combination of A and B. The 3 of them together just sort of, they have a synchronicity, they have it's the right word for that. The 3 of them together become extremely powerful. All right. So the one thing that's missing right now is understanding what part 2 says. So we've got to discuss the Euclidean algorithm, and I think that will be the end of this segment. So yeah, that's right, that'll be the end of this segment. So we'll be leaving a last section in chapter 2 for the end, Bezout's identity, for next week. So what is this algorithm that ancient Greek mathematicians foresaw our need for today? First of all, the Euclidean algorithm finds GCDs. And it's in a category of algorithms that's kind of special, where recursion is available to us. It's a recursive algorithm, which means that essentially you have a problem to solve, and you can solve it provided you could solve an easier problem. So then you can solve that easier problem, and maybe that's the same way. You could solve that one, provided you could solve an easier problem than that. So you recurse your way down until you get something that's totally trivial, and then you go, well, that answer we just got in the trivial case was the answer in the original case. Well, you'll see how this works when we actually do the Euclidean algorithm. Let me just tell you the setup. You're gonna have A and B, like we've always been using A and B as these random numbers that we're dealing with. You're gonna write A as QB plus R. That's fine. Here's this weird fact that makes the Euclidean algorithm work. The GCD of A and B is exactly the same number as the GCD of B and R. Okay, maybe that's weird, maybe that's not. I don't know how strange you find that, but if you accept this, think about what it says for you. A and B are relatively large numbers, but I know R is smaller than B. So, okay, each of them has a B in it, each of these expressions has a B, but R is smaller than B and A was bigger than B. That's the way we normally think of this, is A is the larger number. So this is an easier instance of the same type of question. And that's where recursion pops up and says, well, if you can convert a hard problem into a slightly easier problem, now solve the easier problem. And you might get to do it again. You might just say, well, when I go to solve this thing, I come up with an easier question which will have the same answer. And again, that might follow. So, wow. Let's try applying. First of all, let me state what the Euclidean algorithm looks like. You're going to repeatedly write the quotient remainder form of the numbers involved. Okay? Then you are going to put B where A was and put R where B was and do the same thing. And you'll keep doing that until you get to something where, oh, it's obvious what the largest common divisor is. Because of this fact, each time I make that substitution, the B's go to the A's and the R's go to the B's, you get another thing that has the same GCD. So, yeah. I probably should try to write out the algorithm in some level of detail. Now, you know what? I think it'll flow better if we just show you an example and you'll get what the deal is. So I'm going to do the Euclidean algorithm with the same numbers that we had before as an example where we did the factorization, 60 and 84. So our numbers A and B are going to be 84 and 60. And basically, the Euclidean algorithm centers on writing this in quotient remainder theorem form, or division algorithm form. So write this as A equals QB plus R. Fine. Then how does that work? 60 times 1 plus 24 gives me 84. Let me check my work on that. 1 times 60 plus 24. Is that all good? 60, 80, yeah, that's 84. All right. So that's just the first step. Now the second step is do the substitutions I mentioned before. Take away the big number, replace it with the small number, and the smaller number gets replaced with this remainder. And now we have to write it as, well, in the division algorithm form. So how does that look? 60. You know what? Doesn't 24 go exactly into 60? No, it doesn't. It goes in twice. 2 times 24, and the remainder is 12. Right. Let's try to go to the next stage. The biggest number goes away, gets replaced with the smaller number, and the smaller number gets replaced with what was the remainder. And now we're actually going to be done, because this is a question where you do have an obvious answer. What's the GCD of 24 and 12? Let's see what happens if you try to write it out in quotient remainder form, or the form from the division algorithm. You get that 24 is 2 times 12 plus 0. Yeah? That's when you know you're finished. You know you're finished when the remainder in one of these QB plus R things comes out to be 0. And what, in fact, is the common divisor of these two numbers? It's the last number you got. It appears here, it also appears here. It's the last remainder. So the GCD of 84 and 60 is 12. The GCD of 24 and 60 was also 12. So, you know, all three of these pairs of things have the same GCD. And that's kind of what makes the algorithm work. Perhaps we ought to do this with a tougher example. So the tougher one I want to try is 234 and 144. We'll calculate the GCD of a couple of 3-digit numbers. All right, so the bigger of them will be A, the smaller will be B, and then we'll write A in the form QB plus R. And we'll trace through the algorithm by just completing a table. So we'll start, 234, the big guy, 144, the smaller guy. How does that work? Well, the double of this is 288, which is bigger than that. So you see that it just goes in there once. Yeah, so 234 is 1 times 144, and then what would the remainder be? Well, it's the difference. You can probably see the 4s are not going to matter. 23 minus 14 is 9. Of course, that's in the second place, so the remainder is 90. So far, so good. Now, how does the next step work? I like to visualize it, to be honest. You always are going to take what's in the B column and throw it into the A column. And the remainder you just figured out is going to replace what was in the B column. So this next step is 144 and 90. And now we have to do the same thing. We're actually looping through a thing, waiting for a final ending criterion, which is when the remainder comes out 0. How many times does 90 to go into 144? Well, it also goes in once. And the remainder is 54. Nice round number, so I didn't really even need a calculator for that, right? What is my next pair of things, the next simpler instance of this thing that has the same GCD as the original pair? It's going to be the 90 is here, and that 54 goes here. You may start to be becoming a little suspicious now, but I cooked this up so the quotients are always 1. That was me. 54 goes once into 90, so 90 equals 1 times 54. And what's the remainder in this case? 36. That's what I think it is, yeah, 36. Add those two and you certainly get 90. Still not done though. We're done when we end up with a remainder that's 0. That's when we'll know we stop. What's called the ending criterion for the algorithm. Great. So 54 and 36 are our next pair of numbers. How many times does 36 go into 54? You guessed it, once. This doesn't always work out that way. I just made it happen because I thought it would be funny. I'm not sure if it's funny, but it's amusing me anyway. What's our remainder now? I think it's 18. Wait, 36 and 18 is 40. Yep, 18. Still not done though. I didn't get a remainder of 0. So the next pair of numbers are 36 comes from there, and 18 comes from here, and oh, do you see that? 18 divides evenly into 36. 36 is 2 times 18 plus 0. You surprised about that too? It was 1, 1, 1, 1, 2. It's like duck, duck, goose. Get up and run. Yeah. That's when we know we're done. And the remainder you got in the previous step, that's the GCD. And you can probably, use a calculator. You can easily verify that 18 goes into both of these. It's a little tougher to show that no other larger number divides both of them, but, well, kind of the point of the Euclidean algorithm is it guarantees that this output is in fact the GCD. All right, we're going to put the GCD algorithm, this Euclidean algorithm, to work in the next section, which I think I'm going to put off to next week. So that'll be in Tuesday's lecture, the lectures for Tuesday. So I'll see you folks on Thursday, and then we'll do that. Okay, bye.